So in this video, we're going to look at the sine function and think about conceptually how we derive the derivative formula, and then we will solve it manually using the definition as well. So, but we want to look at it as a concept first before we start delving into the algebra of it. So this is a graph of the sine function. And we see it's 0 at 0 and 1 at pi over 2, and then back to 0 again at a little bit more than 3 at pi, and so on and so forth. This is our typical y equals sine x. Now, if we want to find the derivative of this function, one strategy that we can use to kind of guesstimate what the derivative has to be is remember that the derivative is the slope of the tangent line. So what we can look at what is the slope of the tangent line to the graph at any individual point, and then record those values and then see what we get, plot the points and see what kind of function we have. So if we plot the tangent line, remember it's a straight line that passes through the graph and touches the graph at a single point. What is the slope of the tangent line? Well, it's the steepest here at, let's say, x equals 0. And if you very carefully measure how far over you're going and how far over you're going, you're basically going over 1 unit step. So this has a slope of 1 at x equals 0. And again, if we look at the slope when we get to pi, we actually end up with a similar slope. It's the same slope, but in the negative direction. This has a slope of -1. And again, you can interpret this from the graph. It's a little clearer to see at x equals 0 because the units of the graph are in nice integer units. This is x, 1 unit over an x. This is 1 unit up in y. You can see very clearly here. Part of our issue is that we're dealing with pi, and pi is not exactly 3. But if you eyeball it, you can see that this is about 1 unit over from where pi was. And this is likewise about 1 unit over from where pi was. So it is, in fact, -1. So we have 2 points that we can plot. F prime of 0 is equal to 1, and F prime of pi is equal to -pi. And of course, we know that pi cycles, so that f of 2 pi, sine of 2 pi is the same as sine of 0, and sine of 3 pi is the same as the sine of pi. And so we have these points now where we have 1s and -1s for our derivatives in this periodic cycle. Now, what about at pi over 2 and 3 pi over 2? Well, at pi over 2, we're at the peak of our sine graph. And this tangent line is horizontal, and horizontal lines have 0 slope. Same thing at 3 pi over 2, we're 3/4 of the way through our cycle. And the zeros here, the horizontal tangent line again, the slope is 0. So again, at multiples of pi over, at odd multiples of pi over 2, you're going to have a slope of 0 for your derivative. So we could fill in this table. We fill in 0 here and 0 here. And then what if we plot these points? What is the chart? What does the graph look like if we plot these points? Well, this is what our graph looks like. Again, these are just the points plotted. And if we follow them in succession, like so, we can fill in the values of the curve. And what we get is a cosine function. So here is our one derivative at sine of 0 equals the derivative at sine of 0 is 1. And at pi over 2, we had a 0 derivative because the slope was horizontal. And then at pi, we had a -1 derivative. And then at 3 pi over 2, we were back to 0 again. And then the cycle repeats. And so this is a cosine function. It's a maximum at x equals 0 is 1. And then it cycles through all of these values. And then it keeps going. So that's the cosine function. Now, that's not really a proof, but conceptually, you can see where this seems to be going. And so we can use the definition of the derivative in order to try to prove, in fact, mathematically, algebraically, that this is in fact the case. And so we're using our definition of the derivative here. And we're going to substitute and do a little bit of algebra. And if we do that, then we get sine of x plus delta x minus sine of x divided by delta x. We need to apply the sum formula for sine of alpha plus beta. Here, alpha is going to be x, and beta is our delta x. And then we substitute that. And the formula did not come up. That is disturbing. But what we end up with is essentially we're gonna get one formula that has both of these terms in it. So we're going to end up with sine x cosine delta x, and then plus cosine of x sine delta x, and then the minus sine x comes from our formula up here. And so what I did for this next step is I simply split them up, sine x cosine delta x minus sine x over delta x, and the sine x, the cosine x sine delta x over here. Now, on the left side, what happens to the cosine of delta x as delta x goes to 0? Well, it goes to 1. And so what happens in this numerator is that you get sine x minus sine x. You can, in fact, factor it out. And basically, you're applying the formula cosine of x minus 1 over x, which, again, we can prove this numerically, or later on we'll prove it with L'Hopital's rule, but that this is 1 and is a 0, rather. And so the sine x times 0 will be 0. And so this limit is, in fact, going to be 0. On the right side, we have this, again, a special limit, sine of something over the same something. That limit, again, we can do it numerically. That is going to be equal to 1 when delta x goes to 0. And it's going to leave us with the cosine x because of this component, this factor. So what that leaves us with, this term becomes cosine x because these become 1. And then the rest of this whole thing becomes 0 because it's sine x times a limit, which itself goes to 0. So what we end up with is cosine x.